Hello students, welcome back. Let's resume our discussion in section 4. We're almost there. First, we established the factor groups for kernels of homomorphisms, but that was just for special case. And then we established the factor groups for arbitrary normal subgroups. And the second method was of course tougher, but it was more general. So in the end, we were able to produce factor groups for arbitrary normal subgroups. Can you think of an example of this? Well, one example I can think of is residue class group, even though it is just an abelian example. Really spectacular example in factor groups and normal subgroups should come from non-abelian examples, you see, because for abelian groups, every subgroup is normal, so it's a little bit less interesting. Still, let's do it one step at a time. One of more typical example is the residue class group. For arbitrary element n of z prime, what is the factor group? Z over nz. You see, z is abelian, so every subgroup is normal. So we can consider factor groups with respect to every subgroup. And this will turn out to be a residue class group. You see? And what is the coset relation here? The normal coset relation. The normal equivalence relation modulo n. A and B are related if and only if AB inverse belong to that subgroup. Let's see, let's open up that coset relation here. Oh, I use this one. Yeah, xy inverse belong to that group, but instead of using the power expression, this is abelian, so let me use subtraction expression. And this will give me right coset, but that's okay because we are talking about abelian groups, so left coset, right coset, they're the same. So equivalence class based upon this normal equivalence relation modulo capital N, and they'll have a factor group, of course, and the factor group is the residue class group, 0, 1, 2, 3, all the way up to n over n minus 1. And then these are cosets actually. So 0 bar is 0 plus nz. So like this. What do you mean k bar in this case? K bar, according to this is k plus nz. It's a coset. As for non-abelian example, well, we're going to consider some further examples down here, but let's do easier problems first and then go to the others. Let's see, we completed section 4, but there's still one more topic to go. You see, we prove that this is well defined and it defines a group through the coset method. We prove that this is well defined through coset computation, like this. You see the coset computation. Now what if we use the second method? Oh, excuse me, I was a bit overboard. What if I use the second method, equivalence relation method? Let's try to prove this is well defined using an alternative viewpoint. So basically, here's a question. Will the induced operation yield the same result when different representatives are taken? So instead of taking different representatives as a coset, x1n versus x2n, kind of like that, let's consider x1 and x2 are equivalent, kind of like that. So instead of taking same coset like this, let's apply this left coset relation, this one here, which we call as normal equivalence relation. So re-express this blue into this and re-express this green into this green. And then of course we have to use the fact that n is normal. In other words, we'll have to use these as well. N is equal to n x1, x2n is equal to n x2, y1 n is equals to n y1, and finally y2n is equal to n y2. This purple relation, which comes from the fact that n is normal. So blue, green, and purple, we have to use these to prove that. So instead of using left coset and this left coset are the same, we are rewriting into this and that are related with respect to this, where is it? This left coset relation. So how do you prove that? How do you prove this? Well, one way to do that, it appears that we can use the inverse formula, and you're going to get y1 x1 inverse. y1 inverse x1 inverse and x2 looks like that's what we are getting. We just use the inverse formula, and then if you use the associativity, you can rewrite it as y1 inverse. Let's remove this parenthesis, by the way, and then let's put parenthesis here. x1 inverse and then x2, and then y2. Yeah, okay, all right. And then is there any way to manipulate this thing a little bit further? Well, it appears that x1 inverse x2, that looks very much like the coset relation. This one here, that belongs to a certain capital N, so certain element of capital N, and which may be named into some N or something. So this is a member of this normal subgroup capital N. And then we have to use this normality property, and then maybe switch order or something so that I can put y inverse y2 like that, so that we have another left coset relation. That's the idea. Let's see. Is that something we can do? Yeah, we use the inverse formula and put the middle together, and then this is a member of a certain n, which is a member of capital N, the normal subgroup. And then if you use the property of the normal subgroup, you can change the order. This n became n prime now, and then that's a member of the previous computation. So this n, the left coset relation again. So member of n, so eventually I get member of n. I think I misused something. Yeah, this one here, n prime, I must have been thinking about this new here. Okay, alright, this character and that character should be the same because this and that are the same. Somehow I made a typo before. Sorry about that. Anyway, yes, we get the left coset relation. So x1, y1 and x2, y2 are related. So they define the same left coset. That's an alternative proof. And that's for the proof of well-defined part, the harder part. And as for the group operation part, the associativity, identity, and inverse, they're going to be much easier, so the detail is left to the students. Oh, the same thing we saw before. Yeah, the same thing. No problem. Okay, that's it. It's really done. We really got everything done. So that completes section 4.